Example 1 is an object with an initial horizontal velocity. A ball starts at a height of 19.6 meters with a horizontal velocity of 10 meters per second. For 2D projectile motion, here's some questions we might see. How far does the ball travel? How long is the ball in the air? And what is the speed of the ball when it lands? These questions are just asking for a value at a specific point in the motion, like when the object hits the ground. But let's start by exploring this motion and come back to these questions later. With projectile motion, it's not really important why the object has its initial height and velocity. In this example, the ball is shot out of a cannon on a cliff, but we really just care about the projectile motion of the ball, so all we need is the initial height and the initial velocity. Now that this is two-dimensional motion, we need to choose the origin where x and y are 0, and which directions are positive. You can set this up differently, but let's place the origin at the ground, directly below the initial position, and we'll say right is the positive x direction and up is the positive y direction. Using this coordinate system, the ball's initial x position is 0 meters, and the initial y position is 19.6 meters. We could also write the initial position using coordinates. As a side note, we're usually describing the projectile motion of an object's center of mass. When we draw a picture, the object is going to have some width and height, so keep in mind that we're describing the center of the ball, so it hits the ground when its center has a y position of 0. The initial velocity is 10 meters per second, and it's in the horizontal direction. That means the initial x velocity is 10 meters per second. The initial y velocity is 0 because this vector has no y component. It only points in the x direction. Since this is projectile motion, the acceleration due to gravity, g, is 9.8 meters per second squared downwards. Since we chose up to be the positive y direction, then ay, the vertical acceleration, would be negative g, negative 9.8 meters per second squared. So that's our setup. Now let's see what this motion looks like. The ball moves to the right and falls down at the same time. What's happening to the x position over time? What about the y position? And what do you think is happening to the velocity in the horizontal and vertical directions? Are they increasing, decreasing, or staying the same? Here's some grid lines and snapshots of the ball's position at half-second intervals. How much does the ball move to the right during each interval? And how much does it move down? If we draw lines from the ball to the y-axis, we can see how the y position is changing over time. The spacing between each line gets longer. As the ball moves, it falls a greater distance in the vertical direction during each second, or each half second. Now let's look at the motion in the x direction. The spacing between each snapshot is the same. The ball moves the same horizontal distance during each interval. So why are the vertical and horizontal motions different? 2D projectile motion is one example of an important concept in physics that we mentioned in a previous lesson. An object's x motion and y motion are independent of each other. The vertical motion does not affect the horizontal motion, and the horizontal motion doesn't affect the vertical motion. We know that objects in projectile motion experience a downwards acceleration due to gravity. Since gravity only acts in the vertical direction, gravity only affects the vertical motion. So if we look at the y position over time, the ball is accelerating downwards due to gravity. That acceleration causes the vertical velocity to increase. The ball speeds up in the vertical direction and falls a greater distance during each second. This should look familiar because it's the same as one-dimensional projectile motion, sometimes called free fall. This is a really important concept. The vertical motion of the ball shot out of the cannon is identical to a ball falling straight down. The initial velocity is horizontal, so the initial vertical velocity is 0. That's the same thing as being dropped from rest, if we're only looking at the y motion. The balls have the same height and velocity at each time point, and they hit the ground at the same time. The fact that the ball is also moving to the right has no effect on its vertical motion. So why is the horizontal motion different? Well, there's no gravity in the x direction, so there's no acceleration in the x direction. Gravity pulls the ball down, but it doesn't pull it to the right or left. If the x acceleration is 0, then the x velocity is constant. It doesn't change over time. So the ball moves the same distance in the x direction during each second. We could think of the ball's horizontal motion as being identical to a ball rolling on the ground at a constant velocity. Or if we turned gravity off, the ball would move in a straight line at a constant speed. The difference between this path and the ball's actual path is the amount the ball falls due to gravity. But the vertical acceleration has no effect on its motion in the x direction. As an analogy, here's a bird's eye view of a curling stone sliding on ice with no friction, which we used in some previous videos. This is 2D motion on a horizontal plane, so the x and y directions are both horizontal on the ground. If we give this stone a push in the x direction, so we give it an initial x velocity, it'll move in a straight line at a constant speed if there's no friction. Now imagine we attached a model rocket engine to the curling stone. When we light the engine, it causes the curling stone to accelerate. If we point it in the negative y direction, the y velocity will increase and the stone will move further during each interval of time. Now, what if we light the engine and, at the same time, we give the stone a push in the x direction? Now the stone follows this curved path, which is a combination of a constant velocity in the x direction and acceleration in the y direction. In this example, the acceleration is caused by the rocket engine. In projectile motion, the acceleration is caused by gravity. This picture will change a little bit when we have different initial values, but this is how two-dimensional projectile motion works. The ball has separate x and y positions, separate x and y velocities, and we use separate x and y equations. But we can take the x and y velocities and combine them to get the actual velocity vector of the ball at any time. We can draw the components like this, or we can draw them so they form a right triangle with the vector. V is the instantaneous velocity vector of the ball. It shows the ball's actual velocity through the air and the direction of its motion at each instant. This might be the first time we're seeing a velocity vector on a curved path, where the direction is changing. Notice that the velocity vector does not trace the path of the object. The path is curved, but a vector is just a straight arrow. The velocity vector is always tangent to the path, and it shows the direction of the velocity at one instant. So now that we have an idea of how things work, let's use the equations and see what the motion graphs look like for this example. Here's the information we have. First, let's use this equation to find the y position at each time point. Like we mentioned in the last video, the first variable in this equation is written as y final. When we solve for the y position at each time, you can think of each one as the final y position in the equation, but we're just going to write them as y with no subscript. At the point where t equals 0.5 seconds, we can plug in 19.6 meters for the initial y position, 0 meters per second for the initial y velocity, 0.5 seconds for the time, and negative 9.8 meters per second squared for the y acceleration. That gives us 18.4 meters for the y position at 0.5 seconds. We can do the same thing for each time point by plugging in the same initial values and the different times. At 1 second, the y position is 14.7 meters. At 1.5 seconds, it's 8.6 meters. And at 2 seconds, the y position happens to be 0 meters. So we can see the y position, the height, is decreasing as the ball falls. Here's the y displacement between each point. The ball is moving further during each interval because it's accelerating. Here's the graph of the ball's y position versus time and the points we just found. The horizontal axis is time in seconds, and the vertical axis is the y position in meters. The line starts at the initial y position, 19.6 meters. It decreases over time, and it crosses the horizontal axis at 2 seconds. That's when the y position is 0 and the ball hits the ground. The graph is a curved line because the ball is accelerating in the y direction. The graph and the actual path of the ball are parabolas, but this graph is not showing us the two-dimensional path of the ball. It's just showing us the y position over time. If the ball was falling straight down, this graph would be the same. It's just showing how the y position is changing. Also, this is a graph of this function, which is the kinematic equation we used with the initial values, and it's written as the y position as a function of time. Now let's find the y velocity at each time using this equation. This tells us how the velocity is changing over time due to an acceleration. When t equals 0.5 seconds, we can plug in 0 meters per second for the initial y velocity, negative 9.8 meters per second squared for the y acceleration, and 0.5 seconds for time. That gives us negative 4.9 meters per second for the y velocity at that time. At 1 second, the y velocity is negative 9.8 meters per second. At 1.5 seconds, it's negative 14.7, and at 2 seconds, it's negative 19.6. Here's what the y velocity vectors look like as the ball falls. They're always negative because they point in the negative direction, but the magnitude is increasing. The ball is speeding up. If we look at the y velocity at 1 second intervals, it's changing by the same amount each second. That amount is the acceleration, negative 9.8 meters per second. And here's the graph of the y velocity versus time. The horizontal axis is time, but now the vertical axis is the y velocity in meters per second. Up is the positive direction, and down is negative. It starts at 0 meters per second, which is the initial y velocity. The slope of the velocity graph is the acceleration, the change in velocity over the change in time, which is negative 9.8 meters per second per second. Here's the y position, y velocity, and y acceleration graphs together. The y acceleration is always a constant negative 9.8 meters per second squared, so it's a flat line. The slope of the velocity graph is the acceleration. The acceleration is negative, so the slope of the velocity graph is negative. And the slope is constant, so the velocity is a straight line. The slope of the position graph is the velocity, the change in position over the change in time. At 0 seconds, the slope of the position graph is 0, and the velocity is 0. At 1 second, the slope of the position graph is negative 9.8, which is the velocity at 1 second. The velocity is changing, so the slope of the position graph is changing, which makes it a curve. Now let's look at the motion in the x direction. There's no horizontal acceleration, so we can use this equation to find the x position at each time. At t equals 0.5 seconds, we plug in 0 meters for the initial x position, 10 meters per second for the x velocity, which is always the same as the initial x velocity, and we plug in 0.5 seconds for time. That gives us 5 meters for the x position. At 1 second, the x position is 10 meters. At 1.5 seconds, it's 15 meters, and at 2 seconds, it's 20 meters. Notice how the x displacement is the same for each interval because the x velocity is constant. The ball moves 5 meters to the right every half second. Here's the graph of the x position versus time. Now, the vertical axis of the graph represents the x direction. The initial position is 0 meters, and as the ball moves to the right, the line on the graph moves up. This is how motion graphs are set up. We always have time on the horizontal axis. This is a graph of this function, which is the kinematic equation we just used. The y-intercept is 0, which is the initial x position, and the slope is 10, which is the x velocity. Notice how there's nothing special about this graph at 2 seconds when the ball hits the ground. The line doesn't stop, cross an axis, or reach some maximum value. If the ground wasn't there to stop the motion, or if there was no gravity, the graph would be the same and the ball would keep moving to the right forever. So if we want to find the x position when the ball hits the ground, which is the range of the projectile motion, we first need to find the time it hits the ground using the y motion. In this case, that's at 2 seconds. Then we can find the x position at that time, which is the range. What about the velocity in the x direction? Well, since there's no acceleration in the x direction, the x velocity is always the same as the initial x velocity, 10 meters per second. The magnitude, or length, of the x velocity vector doesn't change over time. Here's a graph of the x velocity versus time. It's not that interesting, but it is another way to show that the x velocity is a constant 10 meters per second. And here's the graphs for the x position, x velocity, and x acceleration. These are just the graphs for an object with a constant velocity, so again, they're not as interesting as the y graphs. The acceleration in the x direction is 0, the velocity is always positive 10 meters per second, and the x position increases over time. Since the acceleration is 0, the slope of the velocity graph is 0. And the velocity is constant, so the slope of the position graph is constant, and it's a straight line. So that's what two-dimensional projectile motion looks like when an object starts at some height with a horizontal velocity. Now that we've looked at the motion, let's answer a few questions. How long is the ball in the air? How far does the ball travel? And what is the speed of the ball when it lands? Let's start with the first one. We mentioned earlier that the time in the air is only determined by the y motion. So we're looking for the time when the ball hits the ground, which is the time when the y position is 0. The only equation we can use with the information we have is this one. We can plug in 0 meters for the final y position when the ball hits the ground, 19.6 meters for the initial y position, 0 meters per second for the initial y velocity, negative 9.8 meters per second squared for the acceleration, and we want to solve for t. We can simplify this equation, add 4.9 t squared to both sides, divide by 4.9, take the square root of both sides, and we get 2 seconds for t. That's the time when the ball reaches 0 meters, and it's how long the ball is in the air. Next, how far does the ball travel? This is asking for the displacement of the ball in the x direction, which is the range of the projectile motion. How do we find that? We know the ball is moving to the right at a constant velocity, and now we know how long the ball is in the air, 2 seconds. That time applies to the y motion and the x motion. That's how long the ball has to move to the right, so we can use that time and the velocity to find the displacement. So let's use the equation for the x velocity. We can multiply both sides by time, and then plug in 10 meters per second for the x velocity and 2 seconds for the time. This equation uses delta t, but that's the same as t because the initial time is 0. When we multiply those together, we get 20 meters for the x displacement, which is the range. We'll talk more about range later in the video. Finally, what is the speed of the ball when it lands? Are we looking for the x velocity or the y velocity? When a question asks for the speed or velocity of an object in 2D motion, it's talking about the actual velocity vector, which is the combination or the vector sum of the x and y velocity components. So the final velocity vector is the combination of the final x velocity and the final y velocity. Speed is the magnitude of velocity, which is the length of the velocity vector. So if we know the components, we can find the magnitude using the Pythagorean theorem. We already know the final x velocity. It's the same as the initial x velocity, 10 meters per second. So we need to find the final y velocity. We could use this equation and plug in the time when the ball hits the ground. Or we could use this equation and plug in the final y position. The first equation only works because we already found the time, so let's use this equation. We plug in 0 meters per second for the initial y velocity, negative 9.8 meters per second squared for the y acceleration, 0 meters for the final y position, and 19.6 meters for the initial y position. If we simplify that and take the square root of both sides, we get 19.6 meters per second. Notice that this equation only deals with positive values for the velocities because they're squared in the equation. So it's really giving us the final y speed, or the absolute value of the final y velocity. The y velocity points in the negative direction, so the final y velocity would be negative 19.6 meters per second. So now we know the x and y velocity components when the ball hits the ground. Remember from the lesson on vectors that we use the Pythagorean theorem to find the magnitude of a vector, which is the hypotenuse. So the final velocity is the square root of the final x velocity squared plus the final y velocity squared. We plug in 10 meters per second and negative 19.6 meters per second, and we get 22 meters per second for the magnitude of the final velocity, which is the final speed. Alright, so that's an example of two-dimensional projectile motion where an object starts at some height with a horizontal velocity.